Good morning, everyone. Welcome to Nano Open Webinar. We have Professor Fang Xu today. I would like to give the floor to our Analytics Services Manager, Dr. Mahmut Taş, to introduce Professor Fang Xu.
Thank you, Nokta. As you mentioned, today we had the privilege of hearing from Dr. Fang Xu, an assistant professor in material science at University of Nottingham. Dr. Xu has obtained her bachelor and master degree in material science and engineering from Northwestern University from China. She then graduated with her PhD in materials engineering from University of Exeter, United Kingdom. Her research has focused on two themes. The first of them, the creation and characterization of novel nanostructures, and the second one is to functional nanocomposite towards advanced applications with particular focus on thermal management and tribological applications. Dr. Xu established substantial expertise on the fabrication and characterization of a wide range of nanocomposite and nanostructured materials. She has so far co-authored over 40 peer-reviewed international journal publications in composite area. Dr. Xu has been guest editors for several journals, including Nanomaterials and Chemosensors. She has been extensively involved in projects funded by EPSRC, Innovative UK, Clean Sky, British Council, and etc. Dr. Fang Xu will be sharing their insights on remarkable enhancement of thermal and electrical properties for polymer composite through a conductive network. We encourage you to engage with the presentation by asking questions and sharing your thoughts in the chat. She will have some opportunity to answer all the questions. Dr. Fang, thank you again for being here today with us. You can now start your presentation.
Thank you very much, Nokta and Mohammed, for the introduction. And it's a great pleasure for me to give the talk today. I will share my screen. Please let me know if you are seeing the right content.
Yes, it looks full size of.
Okay, it's the first page, right?
Yes, first
Thank
page.
you very much. Okay. So thank you very much for this opportunity. It's my great pleasure. So I'm going to talk about a remarkable enhancement of thermal and electrical properties for polymer composites through a conducting network. So before I start to talk about what I'm doing, I would like to introduce where I am from and who I am. So I'm from University of Nottingham. So we are in city of Nottingham in UK. And let me get my pointer. Oh. So sorry, if you don't mind, I will end the show and get my pointer. Why I couldn't get my pointer? I do need my laser pointer. Sorry, if you don't mind, can I stop sharing now and get my pointer back first? It's not here. Excuse me, I couldn't find the laser pointer in this mode, so we'll go with it. Okay.
Okay.
There's no, I tried the laser pointer earlier, but I can't get it back. Anyway, so the top left image is our old market square. This is our city hall. And And the city, Nottingham City, is very famous for the legend of Robin Hood and Brian Clough. So he is if you are a big football fan, you should have heard about Nottingham Forest, and he was once manager for the Nottingham Forest football team. And this middle image is believed to be the oldest pub in England. So where are we if geographically? So this is the map of UK on the right, and Nottingham is to the north of London. It's about 1.5 hour train to the north of London. So this is Nottingham. So University of Nottingham, we are very proud, is the truly home for international students. We have 3 campuses across the world. Our main campus, of course, is in UK, in Nottingham. Actually, in Nottingham, we have 3 campuses as well. We then have another campus in Malaysia. Malaysia campus has more than 15 years now, and it's one of the best 2 universities in their country. We have China campus in Ningbo. It's quite a big university as well, and it has very good reputation at the moment. We are very proud. So this is University of Nottingham. About myself, thank you for Mohammed. He has already gave a very comprehensive introduction, so I'm not going to repeat everything here. Thank you, Mohammed. So my research has been focused mainly on creation and exploration of of nanostructures and nanocomposites. So the nanostructure that I have been worked with, including from left to right, 0-dimensional nanoparticles, like inorganic fullerene, tungsten disulfide, and 1-dimensional nanorod, nanowires, examples including zinc oxide nanorod, tungsten oxide nanowires, 2-dimensional nanosheaths, 3-dimensional hierarchies like graphene skeleton, and carbon nanotubes grown on ceramic foam or metal foam, and also focus on bulk nanocomposites, including inorganic fullerene, reinforced nylon 12, and also graphene oxide and carbon nanotube reinforced aluminum ceramic composites. So the technology we are using, including chemical vapor deposition, this is how we grew our carbon nanotubes on ceramic foam. Hydrothermal, this is what we use to grow our tungsten oxide nanowires. Atomic layer deposition, this is how we grow those very ordered zinc oxide. And soil gel, physical vapor deposition, chemical exfoliation. Normally we use this to prepare graphene layers. Hot press, sparkling plasma sintering. Those 2 technologies are what we use to prepare our ceramic composites and metal composites. So my PhD was focused on the inorganic fullerene tungsten disulfide because it's a super shock absorber and super solid lubricant. So in this talk, I'm going to focus on composites with improved thermal conductivity and improved electric performance. And I'm going to give a very brief background first, then talk about how to prepare the thinners for the composite. After that, we're going to show some examples for composite preparation. Then comes the conclusion. So today, the talk audience are for our nanotechnology and the application center. So I'm not going to talk too much about nano technology background because everyone is an expert here. Some of you even more familiar than me for carbon nanotubes and graphene. So since the discovery of carbon nanotubes by Ejima in 1991 and the discovery of graphene by Novoselvo in 2004, this one-dimensional carbon nanotube and two-dimensional graphene had attracted great interest. So they have exceptional properties. Here, we are most interested in its thermal conductivity performance. Compared to conventionally thermal management materials, thermal conducting thinners, carbon nanotube is theoretically believed to have up to 6,600 watts per meter Kelvin thermal conductivity, and experimentally about 3,000 has been measured. Graphene nanosheets is believed to have 5,000 watts per meter Kelvin. This is exceptional. But how to make the best use of their thermal conductivity? A possible routine is to incorporate them into composites. However, to date, the thermal conductivity of carbon nanotube or graphene reinforced composites is not satisfied. It's not as good as we expected. If we look into more details, we would find that the main barriers are two-folded. So first barrier is the poor thinner dispersion, because of the pi-pi interaction between the different carbon layers and the van der Waals forces between the carbon atoms. So it's very easy for graphene or carbon nanotube to agglomerate together, and also the weak interfacial bonding between the thinner and the composites. Both of these will result in local stresses and interfacial thermal resistance. Both the local stress and interfacial thermal resistance will do harm to the thermal conductivity improvement for the composites. So they are not good. Those are the two main barriers we need to overcome. To solve this problem, we propose to find a more effective dispersion strategy. So from the theoretic study by other researchers, we have found out that if graphene and carbon nanotubes mix together, they will work with effective spacers to separate them. Okay, so we propose to combine graphene and carbon nanotube together. Those basic chemistry insights indeed shed light on this poor dispersion issue. But how to solve the weak interfacial bonding? Here we propose to use a molecular level mixing to introduce nanoscale metal coating onto the graphene and carbon nanotube structure. Okay, so to achieve the metal coated graphene nanotube, we will see how we are doing with this. Okay. So hopefully, if we could get satisfied dispersion, if we could achieve atomic level coating, hopefully we will see something promising. Okay, so now let's move to preparation of the hybrid nanostructure of carbon nanotube and graphene to check whether it indeed can help with the dispersion. We all know that if we mix something in solvents, when we dry them, they tend to agglomerate again, no matter how well they have been dispersed in the first instance. So we propose to using a method called the freeze drying approach. What we are doing here is we put we choose graphene oxide rather than graphene because it's easier for graphene to be dispersed in water, and we can then reduce graphene oxide to achieve reduced graphene oxide. So we mix graphene oxide and carbon nanotube together in water using ultrasonic probe. We mix them for required time. So they are very well dispersed in this solution, okay? So in this scenario, they are well dispersed, we hope. And then we put them in liquid nitrogen environment and freezing. Sorry, my alarm sound. And use them freezing drying to dry them. So we are expecting during the solvent or water sublimation period, the structure, the well-dispersed structure will be kept rather than agglomerated together, like compared to the conventional drying method. Okay, but we need to check whether we have achieved what we expected. These are the nanostructures. A and B are the nanostructures achieved immediately after the freezing drying, and C and D are after the reduction process. Okay, so if we look at A and B, we can see very thin layers of graphene oxide, and we can see on the surface there are carbon nanotubes attached because of the pi-pi interaction. But because of the attached carbon nanotube on the surface, the graphene restacking didn't happen because the carbon nanotubes stopped them and works as a very effective spacer. Okay, so we reduce the nanostructure in a hydrogen environment in tube furnace. After that, we can see those thin layered structure has been retained as well, and we can observe carbon nanotubes as well, which means agglomeration didn't happen during reduction process as well, and we indeed achieved the reduced graphene oxide and carbon nanotube structure. But how well the graphene oxide been reduced, we will have a look as well. Okay, so we use XPS to study the as freeze dried graphene oxide and also the reduced graphene oxide nanostructures. Okay, so the red one are the reduced structures. If we compare B and C, we can note that the oxygen peak has been reduced. This is because those oxygen group in graphene oxide have been removed. If we either look at the survey scan or look at B and C, we can notice that oxygen, this blue one and the green one, has been largely dropped because it's already been removed during the reduction process in hydrogen. So we can be confident to see we achieved the reduced graphene oxide and the carbon nanotube structure. We also would like to check how well is the dispersion. So we use BET to measure the surface area for each sample. From left to right, we can see we started to add carbon nanotubes into pure graphene. This is 5:1, 1 portion of carbon nanotube into 5 portion of graphene oxide. We keep adding carbon nanotubes, and then the last sample is pure carbon nanotube. We can see there is a slight drop of total surface area when we add a little bit carbon nanotube. This possibly could be some those small amount of carbon nanotubes being wrapped up by graphene oxide. So total surface area being reduced. But if we keep adding carbon nanotubes, we can see the surface areas increasing and reach 257 square meter per gram. But if we remove graphene oxide, it will drop again. Okay, so when we do this experiment, we keep the mass the same. For example, we use 10 milligram in total weight. So we use either we use either 10 milligram of graphene oxide at the left end or 10 milligram of carbon nanotube at the right end. So we can see actually carbon nanotube do have larger surface area than graphene oxide if we prepare them in this method. So we have confirmed that mix them do help with surface area, do help with dispersion, okay? So we are going to stick with this method. Now we have got pure graphene oxide and carbon nanotube structures. We need to consider how to introduce metal nanoparticles onto the surface because we want to improve the interfacial bonding as well. What we are doing here, we still stick to this preparation method, but we would like to introduce metal particles. The first step are still the same. So we mix graphene oxide and carbon nanotube using ultrasonic probe. In the meanwhile, we prepare metal ion precursors. So it could be many different metal salts, okay? We're going to talk about them one by one. So examples here like silver, nickel, copper. So we have silver acetate in this case, nickel acetate, copper acetate. So we just dissolve the salt into water and we pour our well-dispersed graphene oxide and carbon nanotube into the precursor, okay? And then we mix the two dispersion, the two solvents using magnetic stirring, okay? After they are well mixed together, we put it into liquid nitrogen to frozen them, and then use our freeze dryer to dry it. After that, we will get metal salt mixed with our carbon nanotube and graphene structure, okay? It should be a 3D structure. After that, we will do our reduction process, okay? So metal ion precursor will be reduced. We will achieve metal particles onto our nanostructure, okay? So we are going to examine what we have achieved. This is an example for copper nanoparticle coated graphene oxide and carbon nanotube samples, okay? So A and B is relatively low magnification, and from those we can see it's actually very uniformly coated onto the graphene oxide structures. If we look at higher magnification, we can see indeed those particles are coated onto the structure, and the fourth TM image shows attachment of copper onto carbon nanotube. Okay, so now we can be confident the nanoparticles are indeed being coated to the surface. Okay, so this is for the copper. We start with copper acetate. And this example is for silver nanoparticles decorated graphene oxide and the nanotube nanostructure. Again, lower magnification images shows the uniformity of the silver nanoparticles, and C, D, and E are the TM images. If we look at C, we can see the very tiny silver nanoparticles are coated uniformly on carbon nanotube as well. So compared with copper nanoparticles, silver nanoparticles has a very small size and better coverage on the carbon nanotube. Copper is not as good because it's more difficult to achieve nano size, the smaller size copper particles, but silver is so much better in this aspect. Okay, and we have the diffraction pattern to confirm existence of silver. And the high resolution TEM showed the silver nanoparticles lattice as well. okay? And we do observe multi-wall carbon nanotubes here. So we have successfully created silver nanoparticles onto our graphene and carbon nanotube structure. Another successful example is nickel. Okay, nickel is also better than copper if we're talking about particle size. So it's quite uniformly covered, even though we still can see some large parts. It might be actually the residue of salt. It doesn't look like particles for some parts. And from the TEM, we can observe existence of carbon nanotubes, multi-carbon nanotubes, okay? And we can see existence of GO here as well. So the nickel particles are attached to the nanostructure. And as we can see in figure D as well, existence of carbon nanotube and the nickel nanoparticles. So we have successfully prepared those metal nanoparticles coated graphene and carbon nanotube structures. What we are going to do with them? We have said we want to make composites, okay? So we need to think about how to make a composites now, okay? So I'm going to talk a little bit more background or research rationale on how we choose our method to prepare the composites, okay? So normally for composites, where we see for thermally conducting composites, we add thermally conducting thinners into a matrix, okay? And those composites compose of thermally conductive thinner and the polymer matrix. However, as we said, the result is not very satisfied because the enhancement is not as expected because there is lack of heat transfer pathways, okay? So those disorderly dispersed thinners, or we see randomly dispersed thinners, don't have an efficient, they don't have efficient thermal transfer pathway. So we can only add more and more thinners in, but we can achieve good thermal conductivity if the loading is as high as like 50 weight%. But this is not what we want because it means high cost, heavy weight, and impaired mechanical parameters. As you can imagine, when the loading of thinner is very good, the mechanical property will drop. So we have done many research, and we are thinking if we, well, this is proposed by someone else, of course, but the idea here is if the aligned thinners, whether it's two-dimensional or one-dimensional shape, if they could be aligned, then most of those energies could transmit through the directional thinner network, okay? So this will reduce unnecessary interfacial thermal resistance, okay? So if we imagine those are those people are the phonons, they are trying to move from one point to another point. If we have phonon expressway, it will be so much easier for them. If they don't, then for those gaps, they will need to jump, and all those efforts the phonons are trying to move from one point to another will means more energy, okay? So the more interfacial thermal resistance. This is one of the disadvantage for randomly dispersed thinners, and we are thinking we would like to align our thinners. There are many different strategies to align the thinners, okay? Examples like fiber-free impregnation, well, this almost for all the carbon fiber reinforced polymer composites, we are actually using this method. Vacuum-assisted self-assembly, that's vacuum filtration. This is one of the methods we are using as well. Mechanical stress-assisted alignment, like what we have shown in the last slide, and tape casting, rolling, okay? We can also consider to apply electric and magnetic field aided field to aid the alignment. But as you can imagine, then the fillets needs to be electrically conductive, and it needs to be magnetically working. We can also use electrospinning. This is what Mohammed is using for his PhD. And we also use chemical vapor deposition. And this is what we use to grow our zinc oxide nanorod, as I mentioned. So many researchers grow carbon nanotubes in situ using chemical vapor deposition, and then they prepare composites directly as well. It's also worth to mention template-assisted alignment. So 3D drying is one of them. We have already introduced 3D drying, okay? So there are many methods, and we have chosen 2 of them here in this talk. Okay, now let's move to one example here. Silver-coated graphene nanotube structures reinforce the PEK composites, okay? So this is how we prepare the composite. Up to here, we have already introduced, we get silver nanoparticles coated GNT nanostructures. We then mix our these nanostructures with PEK in acetone. So we disperse them together, and then we dry them. We press them into a pellet, okay? From the XRD, we can see that indeed silver and the PEK has been well pressed together. So those peaks with star are for silver, and those peaks with the triangle are for PEK. Okay, so in order to study the composite well, we have prepared some reference sample. So we have prepared a pure PEK sample. We have also prepared a pure GNT reinforced PEK sample, which means no silver coating on the GNT. We have also prepared a silver reinforced PEK sample, which means we mix the silver particles directly with PEK, there isn't any GNT involved, but we are still following the same process. The silvers are still being produced from reduction of silver acetate to make sure all the materials, all the composites are prepared to follow the same procedure. These are the microscope images, okay? So the left are the SEM, but the ACE on the left side of the SEM are secondary electron images. Because silver is quite heavy, so we use backscattered images to look at the silver particles as well, as shown on the right column of the SEM. Okay, we can see they are very bright, and we can see they are quite uniformly dispersed if we look at relatively lower magnification. TM images confirm the existence of silver particles and graphene and nanotube structures. So this is PEK matrix, silver and GNT here. And we do observe carbon nanotubes as well here. This is a cross section of carbon nanotube, okay? We use TGA and DSC to study our prepared composites. So after the TGA, we can see that different weights has been left over after high temperature TGA. Those leftovers should be silver nanoparticles, okay? And some residual PEK, of course, okay? And the DSC shows melting points are quite similar as well. There are some slight shifts from left to right between pure PEK and our nano composites, but they are still quite similar. From the table, we can see it's just less than 1 degree difference for the melting temperature, okay? But we will see how different they are in terms of properties, okay? So we measure the thermal diffusivity of those materials, as you can see here. And then we measure heat capacity. Using this equation, we can get, so with the thermal diffusivity and the heat capacity and the density, we can calculate the thermal conductivity, okay? We can see thermal conductivity has been improved if we compare pure PEK and silver GNT reinforced PEK. There is about 60% improvement, but it's improved anyway. I mean, whatever composite it is, okay? We have also measured the electric resistance. It's very well worth noting, the electric resistance has been improved largely, if this is what we want, okay? So pure PEK is 5.8 times 10 to the order of 10, okay? So the resistance is very, very high. So it's definitely an insulator, okay? If we add the silver particles, it just improved a little bit, okay? If we using graphene nanotube structure to reinforce PEK, the electric resistance has been reduced to 180, okay? And then if we use silver coated nanostructures, it's only 11. Okay, so the electric conductivity has been largely improved from 10 to the order of 10 level to 11, okay? This is very well worth noting. We have also noted a very interesting fact. When we heat up, if we look at the right images, when we heat up the 4 samples, 1 pure PEK and 3 composites, obviously, after 400 degrees C, up to 400 degrees C, we can see PEK has already shrinked and changed its shape. Silver reinforced PEK changed its shape as well. And but the other 2 composites has returned its shape, okay? Which means it has very good thermal stability. So to better study the thermal duration, thermal stability of the composites, we have used TMA to study how well it's to keep its shape at high temperature with loading, okay? So we can see with loading increase, well, at 1000 Pascal, sample A and B lose its shape, okay? So it's been melted. C and D keep its shape. And then if we increase into 5000, C has slightly lose its shape, which means slightly melted. But if we increase to 10,000, all the 3 samples A, B, C has been melted. But D, the silver coated graphene nanotubes, still keeps its shape, which means the thermal durability is very good. So we're trying to understand why this has happened. We can see for silver reinforced PEK, the silver particles are randomly isolated, separately dispersed in the matrix. Okay, so it's very difficult either for the electrons or for the phonons to travel, okay? But for silver-coated GNT reinforced PEK, there is an expressway either for electrons or phonons to travel. This is why the thermal conductivity has been improved by 50%, but the electrical conductivity has been improved by 10 to the order of 9 times better, okay? So this is something we could always think and maybe we can transfer to other materials system. This is one example, okay? Another example we would like to talk about is the nickel decorated GOCNT mixed with epoxy resin. There's not much we can do when we prepare PEK composites because it's not in melted form. But for epoxy resin, there are some more we can consider. So the first part is still to get the nickel coated GNT, but then we mix this structure with epoxy resin because nickel is magnetic. Yeah, so we then add the magnetic field. We place our mixed resin and nanostructure here. Okay, this is a PTFE mode. So we are expecting to control the alignment of this nanostructure. We are expecting to get this structure. Okay. And the XRD TGA showed what we are expecting. I'm not going to talk too much detail because I can see I'm a little bit behind the time. So this is the SEM. So we have also prepared a reference sample. So on the left, those samples are randomly distributed nickel GNT reinforced PEK without application of magnetic field. On the right is with magnetic field, okay? So we can see, and this is the magnetic field direction, okay? The red arrow. So we can see there is a trend of alignment for the nickel GNT structures to be aligned in the structure, okay? So again, we measured its thermal diffusivity and thermal conductivity, and we can see here. So the black dot here is the randomly distributed GNT PEK, okay? The schematic on the right. So the red top curve is for the magnetic field controlled one that in the symbol is M here, okay? PEK is only 0.1, but the magnetic field controlled ones is 0.46. So it's a few hundred times improvement if we're talking about thermal conductivity. Again, we measured its electrical resistivity. So the thermal conductivity or the electrical resistivity has been largely changed as well, okay? Not as promising as the silver GNT nanostructures though. So we have also measured the CTE because a coefficient of thermal expansion is also an important property for thermal management materials. We want lower CTE. We always want a lower CTE if we put them in a system. We want it to be better matched with other materials, but polymer always have high CTE, so we want to reduce them, okay? And we can see here the magnetic controlled sample has lower CTE compared to other samples, okay? So we also try to understand the CTE, why the CTE has been reduced after we apply magnetic field, okay? If we look at the right sample here, so the randomly distributed GNT and epoxy resin, So when temperature changed, when temperature increased, it can be freely expanded. But if we look at the left one, the expansion will be constrained because of the aligned nanostructure. Okay, I hope it makes sense to you. So we have produced those nanostructures. We have tried to combine them with polymer matrix to produce composites. Okay, but we have also noticed without combining them into polymer matrix, we can still make use of our metal decorated structures. The first thing we have tried is to use those nanostructures to remove dye. Okay, so we mix them in water first and then put them into dye. We use rhodamine B here. Okay, so we can see after 120 minutes, it has been largely reduced. But this is only in dark. Okay, but if we then transfer it to the UV light, it can be further reduced as well. Okay, so if this is 1, okay, it's been reduced from here under dark. If we apply UV light, it will be further reduced, and this is only 0.15 left. Okay, which means very few, only very few rhodamine B have been left over after this. Okay. We have tried to understand the photo degradation mechanism. So we tried them with different scavengers sample. This is just to help us understand what is the mechanism here. Is that the OH works or the H works? Okay. And here we trying to work out its mechanism. We can see it actually can be excited to generate electrons. Okay. Because we're slightly behind the schedule, so I'm not going to explain in more detail, but please feel free to ask questions in the chat. Okay. Oh yes, it's worth to note that for the nickel decorated GNT, there is another advantage. So after we have done the dye removal, it's always difficult to recycle them. But for nickel decorated GNT, we can use a magnet to easily remove those nanostructures, and so we can recycle them easily. Okay. Okay, so here comes the conclusion. So we have confirmed that graphene and carbon nanotube work effectively as a spacer for each other. So we can combine them together. We can get better dispersion. And we have using molecular level mixing and freezing dry method to work effectively, construct and decorate graphene and carbon nanotube hybrid structures. A wide range of metal nanoparticles can be coated onto our structure. I only talk about copper, silver, nickel here, but we actually have tried many more, like magnesium nanoparticles, many different types. And we actually have tried other application as well. For example, our nickel coated GNTs, we have been using it for gas sensor. It has good properties as well, even though we didn't publish that results yet. So we use those structures can be used as photo catalyst for wastewater treatment, as we shown in the rhodamine B removement. And those structures can be used as reinforcing filler in polymer composites, like the silver coated GNT. And nickel GNT nanostructures reinforce the epoxy resin composites. We have seen that in another example. So those work are carried out or with the help of my colleagues and my students, my postdocs. And this work is supported by different sponsors as well. Here I attach the list of the papers that is relevant to my talk, okay? So everything I talked about today could be found in those papers here. Thank you very much for your attention. Now it's question time. Thank you.
Thank you.
I have questions.
Yes.
Thank you for the presentation. It was a very interesting talk, actually. And I need to ask several questions. One, why did you choose PEEK as a polymer, and what was the application?
That's thank you. That's a very good question. Well, PEK is actually quite a special polymer because the most interesting property is the high temperature.
Mm-hmm.
So PEK can be used at a very high temperature. This is why it's always of interest for high temperature applications.
Okay. And can I continue?
Yes, of course.
In your presentation, I think it was page 29, I saw one TGA result. I would like to talk about it. The remaining part is very high, but it was about 30%. But the nanoparticles you used was not that much. How do you explain this weight residue?
Yeah, let me find the
29, page 29.
Page 29, okay.
29, yeah.
Okay, wait. Then let me go back to my slide again. 29. Can you see my screen actually?
Yes, I can see that.
I can't move it. I don't know. Oh, okay. I can't move my screen. That's very strange. Don't know why.
Maybe you need to make it full screen. And now it works.
Is it this one?
Even here, yeah. If you look at 1 and 4, the weight loss amount is about 30%.
Yes. Well, actually, it is 30%.
Yeah.
If you see here, it's 10, 20, 30.
Yeah, you use 30% of nanoparticles, you mean?
That's a good question. Let me try to refresh myself. It should be in total 30%. I mean the nickel and the carbon nanostructures in total.
All other than polymer, you mean?
Yes. Yes.
Okay, now it's understandable.
Yeah,
I thought you added very small amounts. That's why I couldn't explain why that much. And I have one more question. You also worked on epoxides, and epoxide is a crusting structure. And PEEK is the thermoplastic polymer. And did you also try to see PEEK alignment, magnetic alignment work? And what is the difference? Why did you choose epoxy for alignment study, but for not PEEK?
That's a good study. Thank you. That's a good question. We actually thought about it as well. Because the PEK we are not using liquid form. We are using the PEK pellet. That's why. So if we would like to use alignment, it needs to be in a liquid form.
Liquid form.
Yeah. So the PEK precursor we are using is the solid pellet. So those are small pellets. But so that's why we didn't try magnetic field for PE.
But you can make it by using PEEK as well.
Exactly.
Yeah.
Yes, this is something we have considered. But you know what? Because I'm not a polymer expert, so we start with sample sense. But what you are talking about is definitely something my student will try in future.
Because one is thermoset system, the other one is thermoplastic system. So it's better to see the difference between these two different types of polymers. And also the molecular weight difference, I'm guessing, should make some difference.
I believe so.
Yeah.
And
Yeah. Thank you.
Yeah, and we also try to apply electric field in future as well, because for magnetic field, only limited particles can work with it. So only nickel, iron, cobalt, those magnetic particles can work with it. But if we use electric field, then many more particles, metal particles, can be applied.
Yeah. Thank you so much.
Thank you. Thank you for your question. Yeah, it helped with our future research as well.
Yeah.
Thank you.
Is there any question? Dear Professor Fang Xu, thank you for your presentation. Thank you for your time. You join us.
Thank you very much, Nokta.
Thank you. Thank you, all participants. We will meet 2 weeks later. We will skip 1st of Nano Webinar in March. We will meet 2 weeks later. Thank you, Fang Xu.
Thank you very much. My pleasure.
Thanks, yeah, it was a great pleasure to have you here. Thank you.
Thank you, Mohammed. If anyone has any questions, you can either look at those papers or email me, please.
Okay. Thanks a lot.
Thank you. Yeah. Bye for now.
Bye.